We are talking about thermal energy and changes of state. Now, there's some fill in the blanks here just to kind of move things along, because I guarantee we've talked about some of this in elementary school. True? Somewhere, your 5, 6, 7, 8 teacher, grade 5, 6, 7, 8 science teacher talked about melting ice. No? All right. And if not, we've all had a little bit of ice in our glass. So this is something we've seen before. So when thermal energy of a substance is changed, we have claimed so far that the temperature has changed. That's what we've done so far. And water can have thermal energy given to it. And when we talk about that, we talk about having a positive delta EH, a positive change in heat energy. If you're in chemistry class, you talk about there being a positive Q value. Fine. Or we can talk about it being taken away. And when we take away energy, we talk about having a negative change in heat energy. In chemistry class, a negative capital Q value. If I put a beaker of water on top of a Bunsen burner, we all just accept that somehow EH has gone in to the water. That's something that we accept. I can distinctly remember being in a grade 9 science class, and my teacher, Miss Knight, talking about what happens when you put that same beaker of water into a bath of ice. And that's what this is. It's basically a big tub of ice. It's an ice bath. By the way, if you make hard-boiled eggs, if you want to make them easy to peel, you boil them first in the hot water, then you toss them into an ice bath. Nice thing about that is that the egg on the inside, the edible part, contracts rather quickly, pulls away from the membrane inside the shell, makes your hard-boiled egg really easy to peel. So if that's a hack that you never figured out before, try it out. It's good. It actually works better if you transfer it from an air fryer, because the temperature of the air fryer is hotter than the temperature of boiling water. And so the contraction is more extreme. But that's an experiment for another day, okay? Turns out that food sciences and chemistry has a huge overlap, right? So here we got this ice bath, and we got this beaker full of water. The question is, in what direction is energy flowing? That's what my grade 9 science teacher asked me. Where's the energy going? Come on. Yeah. Into the ice. Yeah, it turns out that this warm water has energy. I'm going to say that it's coming out of the water. It's going into the ice. It's coming out of the water. And that actually brings up the conversation that my grade 9 teacher asked. She said, so when you open the door in the winter, are you letting the cold in or are you letting the heat out? Of course, what's the answer? Anybody know? Yeah? Yeah, you're letting the heat out. You're letting, because energy is a thing, right? Coldness is the absence of energy. You can only unload a thing. You can't unload the absence of a thing. Okay, so we're letting energy out when we open the door. And so if your parents say, close the door, you're letting the cold in, you can turn around with a smile on your face and wink and say, nah, I'm letting the heat out. And then you'll close the door because you're an obedient kid, right? Do the right thing. All right, so I already went through this fun fact about how 1 milliliter of water is equal to 1 gram of water. And you can look through that yourself, all these equalities of masses and volumes and how we've based our volume system on the density of water. And so that's an important thing to know. But we've already kind of conversated about that. I want to talk about this other thing that we've talked about, maybe not in this class, but certainly in grade 6, 7, and 8, somewhere along the line. Somebody talked about this. If I go from a gas to a liquid, what's that called? I'm going to look for hands. Yeah? Condensation. Yeah, it is. It's condensation. All right, so I've got condensation when I go from a gas to a liquid. If I go from a liquid to a solid, what's it called? Yeah? If it's water, it's freezing. Yeah. Now, I want to contest that a little bit, that we're going to call it solidification. But specifically with water, since it's such a common material, we talk about it as freezing. Now that's like case specific. And the reason that I want to draw attention to the case specificity of that is that when I take molten iron and I let it cool down, I don't say that the iron has frozen. I say that it's solidified. Okay, so that's all. It's just like not a big thing. It's just that We deal with water so often that we think freezing, and probably we learned that in elementary school because the teacher was probably just trying to make it easy for us to understand. I get that. Here's one. When gas goes to a solid, it can go directly to a solid. What is it called? I bet you they didn't do this one. Yeah.
Sublimation?
Ooh.
Or is it the other one?
You know what? When it goes from, I'll do this in red. When it goes from a solid to a gas, notice my color coding. Red is when things are heating up. Blue is when things are cooling down. When it goes from a solid to a gas, sublimation. But when it goes the other way, when it goes from a gas to a solid, there's a D word. You know when you make a deposit? Deposition. Yeah, deposition. And I somehow, and it happened in my own kids' elementary school, they never mentioned the word deposition. That's cool. But now you know, okay? It's just a word, deposition. Now, as I look through this, somebody one time said to me, "Oh, this looks kind of like French, you know? Condensation, deposition, solidification." Yeah, it is. There was a character on Saturday Night Live one time, Cajun Man, played by Adam Sandler, and all the answers were "chant" at the end. And yeah, when you do changes of state, everything is a chant. Everything has that sort of French sound to it, that chant. Solidification, solidification, sublimation. And with that chant suffix, I'm going to put my red on again. When I go from solid to liquid, I know there's going to be people that say melting. I'll put that in brackets. But of course, that's specific to water and some other things. But what do you think the chant word would be? Yeah? Liquefaction. Or more French, liquefaction. Right? Yeah. En français, c'est la même chose.
Oui,
Right.
oui.
Yep. Liquefaction. Forgive my accent. Okay? From liquid to gas. What's the chant word? Yeah?
Evaporation.
Yeah, evaporation.
Oh, great.
Right. And you don't want to eat things that are too hot, or else you get indigestion. So here we got. Oh, sorry, I had some hot food last. No, TMI. Never mind. All right, so we've got these different vocab words, and these are vocab words that I would expect people would kind of know moving forward. Some of them you've learned in elementary school. Some of them you haven't. It's helpful to remember that there's a chant at the end. And honest to goodness, if you have a hard time remembering the words, draw yourself a little wheel like this. It's very elementary, but it really helps with the vocabulary, okay? Especially if English isn't your first language, or if somehow you missed that in elementary school. Like, it's nice to be able to go through this. And I'm being silly about the chant and the French thing, because what I found is if I'm a little bit silly about it, and I mention this chant thing, somehow it sticks in people's brains a little bit better. It's not because I'm really like trying to go off on French or Latin or Spanish or something like that. It really is because I want to make sure that it's stuck in your head that they all can have the suffix of chant. Okay, here's another thing.
H20.
I got this temperature chart. It says figure 1, temperature in degrees Celsius versus thermal energy input in joules for H2O for phase transitions. Boy, that's a real mouthful. What I want to say is that I could take something like water. Let's just say that this is water. And I feel like there could have been an addition to this in water. If I wanted to be even more explicit about my title. And what I know about water is that I could have water at minus 20 degrees Celsius. If it's at minus 20 degrees Celsius, what's it called? It's not called water usually. What's it called? Everybody together. It's called?
Ice.
Ice. So at this point here, it's called ice. Maybe you've never thought about this before, but it's true. Ice can be colder than 0 degrees Celsius. And that makes sense. Like, it makes sense that I could take a block of ice that I make in my refrigerator, maybe at minus 5 degrees Celsius or something, and leave it outside when it's minus 20. And it wouldn't be ridiculous for my ice cube to get even colder and become minus 20, right? It would just sit there and it'd get colder. Now, the thing is, if I add heat to that ice cube, I mean, think about this diagram that we got up here. We were talking about adding heat to ice. We were removing heat energy from water, but we were adding heat energy to ice. If I add heat energy to ice, then its temperature is going to go up, 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 up. Notice that the heat energy is increasing, the temperature is increasing. You can actually warm up ice. This happens at the end of winter. The ice warms up. It used to be minus 20 midwinter. Oh my gosh, I hate when it's that cold. But then it gets warmer, warmer, warmer. Now something happens though. And actually, you know what? Maybe I should add in an equation. During this transition, I would say the change in heat for that block of ice would be equal to the mass of the block of ice times the heat capacity of the ice. Now, this I is for ice, it's not for iron or something, it's specific for ice, times the change in temperature for that ice. Okay, I'll make a little note. I equals ice. Okay? Now, I get up to the point where it gets to 0. And one time I was on a scaffolding. This seems like a weird departure. I was standing up on scaffolding, I was doing some painting. And it was like sort of for a community thing. And my friend was at the bottom, and he was shaking the scaffolding. And you can imagine my surprise. I'm like, "What the heck are you doing, buddy?" And he's shaking the scaffolding. And you can just imagine, like, here's the scaffolding. It's like basically platforms and pipes. You don't have to draw this or anything. I got a person up here.
Is that you?
That's me. And I got a person down here. Fine friend that he was, Dave. And he's shaking the scaffolding. Shake, 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 shake. Now, the scaffolding in my situation was actual scaffolding. Scared the heck out of me. Can you imagine if this guy shake and shake and shake and shake and shake, eventually the pipes would fall apart? Like they would actually come disconnected, right? And they would all fall apart in like a pile of free-floating pipes before they fell, right? In the case of ice, back to where I was going with this. As I'm adding energy, would you believe that the crystal lattice of ice is shake, shake, shaking? Kind of like my friend.
Interesting.
You picture it? Shake, shake, shake. That's what kinetic molecular theory says. The fact that it's ice tells me it's a crystal. It's a structured thing, like the lattice, like the trellis, I should say, that I'm standing on, or whatever you call it, this scaffolding. At this point, it turns out that it doesn't fall apart right away. You have to actually keep on shaking it. And you actually keep on adding more and more and more energy. But can you imagine that my friend could shake, 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 shake a lot? And it would get to the point where he's shaking a lot, but my scaffolding doesn't quite fall apart because it's a well-built scaffolding. This is what happens with ice. We keep on adding energy to it, and it actually keeps on shake, shake, shaking harder and harder and harder, more and more energy. But you get to a point where you're shaking it harder and harder and harder by adding more energy, but it actually doesn't break apart yet. You're in a transition zone. Okay? So this transition zone is called the fusion energy. Turns out that you have to overcome the fusion energy to break apart the scaffolding, to break apart the crystal lattice. You have to add more and more and more energy. Keep on shaking it harder and harder. So notice that I've transitioned. I've gotten all the way up to 0 degrees Celsius, and then I added more and more energy, but no temperature change. Just shaking it harder and harder. Eventually, though, if my friend did shake hard enough, the pipes would all fall apart, right? And that's what happens with ice as well. Eventually, you reach a breaking point. The ice lattice, the crystal, breaks apart. And then it becomes, well, what does it become next? As soon as it breaks apart. Starts with a W. Rhymes with otter. Water. It is called water. Right? And it's going to stay water until it gets to what temperature? Yeah?
100 degrees Celsius.
100 degrees, baby. Look at that. Right at 100 degrees. I'm going to add in another equation because we got delta EH, while it's water, is equal to the mass of the water times the heat capacity of the water times delta T for that water. W is for water. Okay? Just for keeping track of things. And what do you suppose happens next? It turns out that water has its own cohesion. It's not a crystal, but intermolecular forces in water. Some of you have talked about water being a polar molecule, maybe in chemistry class. Some of you haven't. But water holds together. Even if you've only looked at it in elementary school, we know that water has a surface tension, right? Water holds itself together. That's why you get that meniscus curve. That's why you can fit lots of drops of water on a penny. Maybe you've done that little challenge in younger grades or whatever. But water has a cohesion, holds it together. And so it's not quite like the lattice because it's not like structured like a crystal. But would you believe you have to shake water apart until the cohesion breaks down? Okay, so I'm using my friend in the lattice as like my analogy here. I know it's not a perfect analogy, but you kind of get the idea because I'm trying to aim for macroscopic mechanical things that we can relate to, but this is happening at a micro level, right? So we add more energy, shake, and then eventually the intermolecular cohesion breaks down. Boom! And this super energized water, by the way, that energy platform is called the vaporization energy. V for vaporization. Look at that. Vaporization. Evaporation. Okay? This vaporization energy, once it gets overcome, then we transition to, I'm going to top out at 130 degrees, not because water actually tops out at 130 degrees, it's just I have to end this graph somewhere. And we get superheated steam. Well, not that super. But the heat energy to get it up to that 130 degrees would be equal to the mass of the steam times the heat capacity of steam times the change in temperature for the steam. S is for steam. Okay? Oh, I should add in some more things because I said them out loud. But F stands for fusion. Not nuclear fusion, but solid fusion, like fusion of particles interconnected by their intermolecular forces, and vaporization. Okay? And this is something you probably never talked about before, because why would you talk about this stuff in elementary school, right? But this graph, this stepwise graph, actually ends up being a diagram for thinking out all these problems. We're going to do problems where you have to calculate stuff. And you're going to have to calculate stuff involving these formulas. And the diagram actually becomes like this visual for you to keep track of it. Okay, so like in kinematics, we drew balls flying through the air. Well, gosh, how am I supposed to draw a crystal lattice of frozen water? I can't do that. But what I can do is draw this graph kind of like a stair step. And the analogy of walking up the stairs is something that helps us to visualize the process of this energy transfer. Everybody all right with this idea? It's me trying to make things more visual for you when it actually is a little bit hard to picture, right? And that's the problem with chemistry sometimes. It's not that it's abstract so much as so small that it's hard to picture. And that can be a challenge for a lot of us. I get that.